Okay. Hello, everyone. It's really amazing for me to be back here at Politechnika Warszawska, and also thank you all of you for coming here. We know it's weekend. You could have been now probably somewhere at Pole Mokotowskie and having fun, but you are here to work at the intersection of AI and security. And this is really great. We are really thankful for your enthusiasm, excitement, and for being here at this time and spending 24 hours to work on our tasks. So this is amazing that you really are willing to go this extra mile and learn more about AI and security. So this actually is our 6th edition of the European Championship. So we already went to many other cities. We went to Paris, we went to Vienna, we went to Stockholm, Barcelona, Munich, and now is the last edition. Come on, guys. Now we are in Warsaw. And this is the 6th edition, and we have done grand finale in Germany to find European champions in AI and security. So this is your last chance to advance to this grand finale. So thank you for being here. And actually, this is our Polish edition of the European Championship. So before we go into details to tell you more about the championship, to tell you more about the tasks, first we would like to here invite Professor Nowak to come to the stage as a host who was willing to give us also this space to organize the whole championship. And Professor Nowak will just say a few words of welcome to you guys. Yeah, Robert, the stage is yours.
Thank you. Hi everyone, welcome at Warsaw University of Technology. It is the oldest technical university in Poland. This year is 200 years anniversary, and I'm from Institute of Computer Science. It's also oldest computer science institute in Poland, and we start building the vacuum tube computers. Now we work on mostly on software, a lot of AI projects and a lot of cybersecurity projects. So I wish you good luck. I hope you enjoy this place, and if you have time, you please visit this building. The main building is really nice inside, built by the Russian Empire 100 years ago. Now it serves for science, and so good luck. Thank you.
Thank you so much. Thank you for the kind words, and also thank you for being here. And now we'll tell you more about first who we are. So who are people behind the championship? So how we define ourselves, especially in my case, is that I am a researcher who travels the world to work on the intersection of AI and security, to work at this cutting edge of AI. And in my case, also, first of all, now I'm at CISPA, where we manage an amazing group of people who are also here with us, students who work on these aspects of AI and security. And before joining CISPA also, I was a postdoc in Toronto, which is really the birthplace of modern AI. And also did my PhD in the US, University of Chicago. I also worked in many companies at Google, Microsoft, you name it. And really, it's still my pleasure to be back here, because I was studying here, a few years ago, let's say, and this was also my alma mater, and I'm really glad to be here and to see all of you kind of like going back to these roots and bringing this cutting edge of research back to where I was studying.
And as of me, my name is Franziska Bönisch. I am currently also a faculty at CISPA, where I co-lead the lab with Adam. And also my research brought me around quite to some places in Europe, in Asia. And what I picked up there is that it's extremely important to consider intersections. Like these days, it's not only about studying AI or it's about studying security, but it's really about understanding when those topics come together and how the one can help the other, how the one can be a risk for the other, and how we need to understand both of them to just create some synergies and thereby solve the big problems of tomorrow. And that's why I'm extremely happy that we're here today. And it's not only us, but we are here with an amazing team of people. And here you see basically our lab, the people who are here. If you just want to briefly stand up and wave, then people can already see. Those are your go-to people during the event today. they have not only developed the whole infrastructure behind the hackathon that's going to run today, but also helped in designing the task, implementing the task, and so they're your go-to experts with any of the technical questions that you might experience over the next 24 hours. So please, like, whenever you need assistance, we will be here for you. But this whole thing would not be possible without a second pillar. And here we have our CISPA administration, our science and talent team, and our communication team, who are also here today, if you just want to wave briefly. So those are the people who really make the operation possible. And I think it's a great chance also to talk to people about opportunities of connecting and of interacting with CISPA more in the future. So if during the event you have any question about the Institute or you have any question about research opportunities, please just approach these people here and they'll be all super happy to assist you. Now, to tell you a bit more about where we come from, it was actually quite away from us, considering that Germany and Poland are actually neighbor countries, but we come from the other end, namely from Saarbrücken, which is a city somewhere between Frankfurt and Paris, actually. And there, we work in a pretty amazing research center, which focuses on two very important topics of nowadays, namely on security and on machine learning. And we there have an extremely international, ever-growing research community of currently more than 700 employees, from more than 60 different nations. And we have more than 40 faculty who, like Adam and me, are leading some research groups on extremely important topics. And one thing that we're very proud of as CISPA is that if you look into CS ranking, so for those of you who are not familiar, CS ranking is a ranking that ranks basically CS-based institutions all across the world based on their research excellence. And if you look into this category of cybersecurity, you will find that CISPA is #1 in the entire world, basically overpassing all the big US institutions. And this shows that we are really successful in what we are doing and that we are really excited about especially these topics of cybersecurity that we will be dealing with today. And the lab that Adam and I run at CISPA is the so-called SprintML-Lab. That doesn't only mean that we work really fast and efficient, but it also means we work on really interesting topics like security, privacy, robustness, interpretability, and trustworthiness. And in our lab currently, we have around 20 people on all different levels, from undergrad students writing their thesis with us to postdocs. And we have a fair share of these people here today with us. So also, if you want to just learn more about their research and about what they are currently excited about, just reach out to them. So without further ado, let's just jump to the details of the event today. And as Adam already mentioned, we're in the 6th round of our European Championship. So this is not an island event, but really an initiative across whole Europe. And this is the final round before we will see who will become the European champion in AI and cybersecurity. And becoming a champion is not only very prestigious, but if you win this entire hackathon championship, you can get big prizes. For the first 3 teams, there are prizes of 4,000, 2,000, and 1,200 euros. But also every runner-up team, so these are the teams, the 3 top teams at every local round, they will be getting a runner-up award of 400 euros. And everybody from the top 3 teams that win here today, basically, or tomorrow, they will be sponsored for their travel to CISPA in July to compete in the final. So if you are among the top 3 people today, you already won your travel and some runner-up prizes. And all you need to do is basically to just go through these next 24 hours with us and give your best. And after our opening session today, we'll be giving some introduction keynote by Michał here. So this is the next point on the road. Then we'll introduce the tasks that are closely related to what you're going to learn in the keynote. Then you can finally get started with the hacking. We'll be there. We'll be supporting you through the process. We'll be having dinner at some point. We were kindly asked to tell you not to eat in the rooms upstairs. So you can eat in the lobby, but food is not allowed in the rooms upstairs. And you're allowed to drink in the rooms upstairs, but if you spill something, then we're supposed to inform people in the lobby because they will come and clean the carpet immediately. So that was very important from the organizers here to mention no food in the working rooms upstairs. But we'll have constant supply of food in the lobby. I think throughout the night, nobody's going to get hungry. We'll also have breakfast tomorrow. And then the hackathon ends on a lunch, during which also the top 6 teams, according our scoreboard, will be preparing their presentations to then, in the final panel, present their solutions. Because if you work 24 hours on something this exciting, you are for sure curious to see how the best teams got to their solutions. So they'll be presenting, we'll be able to ask our questions, and then the jury will meet to determine the top 3 teams that will basically advance to the final.
Regarding the jury, so actually we have in the jury 2 professors from also here from university. So we have Tomasz Gambin and Piotr Gawrysiak. And also we have our CISPA technical team, and all these members of the jury will be assessing the tasks. So for you, during these presentations, we expect that each of the 6 best teams would deliver 6-minute talk. And then I can also reveal we have 3 tasks for this hackathon. So we would expect you to devote around 2 minutes per task. So this is at the very end of the event to also, for you to find out how others solve the task. So you can ask questions, how it was solved. So it's also for you to learn really afterwards how to really solve these tasks, or what is maybe better or even worse solution that you found out during these 24 hours.
So there's one other thing. If you want to communicate with us during the event, we have this Discord channel. I saw that many people have already registered, so I suppose most of you are already there. But if you're not, then this is your chance to join, because this is where all the announcements are going to be made, where questions about the tasks are going to be posted, where all the material, including this introductory slides, are going to be shared. So if you're there, you'll be informed about everything that is happening. And now let's look into the next thing. This is our famous leaderboard. So this leaderboard will guide us through the entire 24 hours of hackathon. Each of our tasks has a separate tab, and all the tasks that we will be giving to you have a score. So it's a numeric score, and this score will be displayed in live in real time at the scoreboard. So you can see how well you're ranking with respect to other teams. There's one thing about it, like if you are familiar with machine learning, which I hope you are if you're here, we do something like train tests, like validation splits. So during the hackathon, we will be displaying the scores on some fraction of the data. So of all the solutions that you submit, like if you submit for 1,000 data points, then it will be the score of like 500, 700, 300, like depends on the task. And then at the end of the hackathon at 12:30 tomorrow, we're going to swap from the validation split to the test split. So we're going to see how well your solution generalizes. So you won't win the hackathon if you just optimize and brute force basically to get the highest score over the scoreboard. But what will really help you will be to develop a general solution to solve the task. And
so maybe at this point, are there any questions regarding this part? So maybe somebody can go to this person with the microphone. So we have, okay.
Hello, the question was, what's the metric score for the evaluation?
We will be explaining for every task. Like every task has a dedicated score, and this score is usually displayed on the scoreboard. So once we introduce the task, we also introduce the scores. And the final ranking is basically a ranking over all the 3 tasks. So what we can also already recommend to you is that it's best to really work on all these tasks. So if you're just really excelling in one task, but you didn't even try the others, then the total ranking, as basically an average of the other rankings, will not be so great for you.
So we will also explain exactly the scoring per task very soon.
Okay.
So just next slide. Okay. Very good question. Any more questions? Okay, it's one more question over there.
Hello, hi.
Hi.
I wanted to ask, are the submissions permanent, like can you resubmit?
Yes, so actually through the hackathon, you can resubmit your solutions. We usually have something like cooldown period of like 5 minutes, and but you can submit through the whole hackathon the solutions. So you can also see live at the scoreboard how your team performs per task, and also overall we have also overall ranking. So actually this scoreboard is for you to get feedback. How good is your solution? Should you try more a specific task, or maybe it's enough?
And what is maybe important about it is also you don't need to worry if you override a good solution with a bad one. We always keep the best solution. So like the best solution is always stored, and then if you score worse, then you don't need to worry that this is going to be like deleting your effort so far, but the best solution is going to be scored.
Okay, any more questions? Oh, there's one more question over there. Okay.
How to find the scoreboard itself? And is it like only the local scores, or is it the number of global?
So the scoreboard will show the scores for all teams. So you will be directly seeing how you rank in comparison. And it's just an API that we expose. We're going to share the URL, and then you just click on that and you're there.
Okay, thank you.
Awesome.
Okay, great questions. Thanks a lot. Okay, so at this point we can move on to the part about, our research. So also background for these tasks for you to solve them. So how I think about that is that nowadays leading generative models such as here we have GPT, Gemini, Llama, you name it, actually they are trained on enormous amount of data. And actually data are very diverse. So they contain, for example, news articles, pieces of music, books, code, images, and much, much more. And actually thanks to this very large number of data points used for training, also we can then use these models to generate high quality content. They can generate functional code, also photorealistic images, and high quality pieces of articles. And now what is really the issue is that in our research we found that actually models are trained on this large amount of data, but actually then they memorize the training samples verbatim. And actually then during inference they can recreate these samples pixel by pixel for images and word by word for text. So what actually we showed is that this is a problem, and as of now there are many, like more than 60 ongoing lawsuits with the claimed amount being more than 90 billion euros. So first of all, it's also the problem because models can generate high quality text which actually can be fake, so other kind of fake data. Then also we have so-called data loops. So models are trained on generated content. So models really is first generated, then it's put online, and then scraped and reused to train new models. Naturally, these data loops, so generating and training on this content, was really shown to cause model quality degradation. So models take the biases from the previous model versions and carry them to the new model versions. And now, overall, what we really aim at is to really mitigate all of these risks. So our goal is to really build a solution that can identify both the training data and also the content which is produced by these models. So here, first we would like to understand what data sets were used to train the models, for example, books or videos. And also on the other side, we want to find out what data actually was generated by the models. And here what we really want to build, our ambitions, is to have a framework which actually gives you some guarantees, in this case, statistical guarantees, to verify if a given data set was used for model training or was generated by the model. And why it's actually important is because, for example, now EU AI Act requires that actually we do this provenance tracing of the data for AI. And actually it's gonna come into effect on August 2028, but of course it's a timely issue that we start working on now. So to really solve this task, it requires us to address these three fundamental questions. And the first question is to really identify what data sets were used to train the models. So this is on the input to the models. Also we have models themselves. We want to understand how models train and how models memorize training data during this process. And finally also we have the output side, where we analyze what kind of data models generated. So we want to find out, for example, by watermarking that a given data point is generated. So first we'll go into this aspect of how to identify what data sets were used for training, and we ask Michał to actually present his paper from iClear this year about data contamination. So invite Michał to the stage and tell us more about his exciting work. And Michał actually is currently working with NVIDIA, and here based in Warsaw. Come on, Michał, come to the stage. And then he is already a distinguished researcher working on these exciting topics. And he will tell you more about data contamination in the models. Okay, so let's go ahead with the lecture. The stage is yours.
Okay, can you hear me? I bet you can. Okay, cool. Nice to meet you. So my name is Michał Zawalski, and I would like to discuss with you some aspects of data contamination, as Adam introduced it, and how we propose a solution to this problem, to detecting data contamination in LLMs. So as you know, currently we all want the best LLMs on the market to use. Because using more capable LLMs, of course, means better solutions, better applications, better user experience, and so on. So how to choose the best LLMs? Of course, the go-to method right now is to use benchmarks for that. But there is this issue that if the model was trained on certain benchmark-like data, then the scores that we use for comparing different models are not meaningful anymore. Actually, do you trust benchmark evaluations right now? Like, everyone is comparing LLMs based on benchmark numbers. So because of that, everyone is benchmarking. And basically, everyone knows that everyone knows. So what can we do about this? Like, firstly, is that really an issue? Like, if everybody knows that everyone is benchmarking, does it matter at all? Well, of course, that introduces a long list of problems. We know that benchmarking is the primary way of comparing between different LLMs, but if the model is trained on benchmark-like data, then if we compare two models on this benchmark, then these scores don't reflect the true capabilities of the model anymore. So this comparison is no longer meaningful. And based solely on benchmark numbers, you can think that a model is better than it actually is. Actually, without any means to detect data contamination, there is no incentive for people to not cheat, like during model development. If you want your model to be on the top of the leaderboard, then of course the easiest way to do this is to introduce some tiny portion of data that resembles to some extent benchmarks to make your model a little bit better. Well, that's of course not moral, that's not ethical, but there is no penalty for that, unfortunately. A really important, good and highly invested effort right now is data curation and synthetic data generation for training language models. Of course, this is a really important effort, but if you push it too far, if you generate too much data, like curate the data set too much, then, you know, if you have a large portion of training data, then which data from this large data set improves your model the most on the given benchmark? Of course, the data that resembles this benchmark the most, which on one hand improves the scores of your model, on the other hand introduces contamination, which is, again, something that we don't want. And even if you want to avoid it, you have no really any way to prevent this, because you never know how much your model is specialized towards a certain benchmark. For example, if I use a model to generate synthetic data for training my new model, if that previous model was contaminated with a certain benchmark and I don't know that because I have no way to check it, then how can I know that my new model trained on this generated data will not inherit this contamination? And still, even though we have all these issues, benchmarking is still the primary way of comparing LLMs, because it is the fastest, the simplest, the most scalable way. So we basically learned to just ignore this problem, which we know it is there. But do we have to do this? Can we do something about it? The question that we asked ourselves is, can we somehow detect whether the given model that we want to evaluate is actually solving the problem that we use for evaluation, or is it using some kind of memorization for giving the answer? And our main finding is that different LLMs react differently to the context during evaluation based on what they've seen during training. And by leveraging this observation, we can successfully detect what was used for training, which kind of data sets were used for training and which were not. So let's analyze an example. Let's take any language model and a data set, for example, GSM-8K. And when we pass this sample from the data set to the model and compute the average log prop of this model on tokens of this question, we get some kind of measure of how confident is the model in modeling this question. Now, what happens if we do the same thing, but give another random sample from this data set to the context? And again, compute the confidence of the model on the same question again. Now, usually, you would expect this context to be helpful, because each data set has certain data distribution. Like, for example, GSM-8K, these are all simple math questions. They have certain vocabulary. They involve some numbers. They all end with a question. They share a certain structure, and so on. So if you give some examples from the data set to the context, you inform the model about the distribution of this data set. So it should be at least a bit more confident in modeling this target question. And usually it is the case. Usually if you give the random sample from the dataset to the context, the confidence of the model on this target sample increases. But it turns out that if the model has seen this dataset during training, this context is not helpful anymore. In fact, it becomes disturbing. And why is it the case? It is the case because, firstly, if the model has seen this dataset during training, it already knows this distribution. So if you give it additional information about this distribution by providing this context samples, it doesn't give any new information to the model. So the model doesn't benefit. And secondly, if the model was trained on this distribution, then it memorizes these samples. And if you put something in the context to the model, then this is not the same sequence that it was trained to memorize. So this context actually disturbs the memorization patterns that the model has learned during training. And because of that, we observe that this confidence on this target sample actually goes down given the context. So this gives us a very simple criterion that allows to distinguish data sets from seen and unseen. So for given any model, any data set, it can be any set of strings, like it can be a benchmark, it can be a training data set, it can be Wikipedia, it can be GitHub, whatever text data. For each sample in this data set, we compare two numbers. We compare the confidence of the model on each sample alone and each sample with additional random context given. And now, based on the difference of those two values, whether this difference is positive or negative, we classify this sample as showing traces of contamination or not. And the final score for the whole data set is the percentage of samples for which adding the context decreased the confidence of the model, right? So each time adding the context decreases the confidence of the model, we find traces of contamination, and based on how often this behavior happens, we quantify what is the amount of contamination for the given language model detected in this dataset. So if the model has seen this dataset during training, we should expect contamination close to 100%, but if this dataset was completely unseen and not even close to the training data, then we should expect contamination of 0% around. Right. So now the question is whether this approach works. And as you can see here, we used for evaluation multiple models with public training data. So for each of those models, we know exactly on which data they were trained, so we can use them for validation. Red dots represent data sets taken from the training subsets of all those models. So data that were seen during training. And blue dots represents data sets that were not seen during training. Well, usually these were some newest benchmarks, recent web pages, books, and generally data created after the models were trained, so something that were definitely not seen by those models during training. And as you can see, our approach provides a really good separation between seen and unseen data. On the dataset level, we achieved AUC exceeding over 99.9%. So this is actually nearly perfect separation between seen and unseen data. In contrast, baseline methods that we use for comparison, they do provide some statistical difference between those two sets, but this is by far not enough to draw any meaningful conclusions. If we have this kind of separation, then finally we can actually get some reliable insights about what the model has seen during training or not. Going one step further, another way to validate this approach is to take any model and fine-tune it on a certain data set to introduce contamination and see how that influences the contamination scores that we compute. And as you can see, we fine-tuned multiple models, even models without public training data, because now we can do this. And in all cases, after just a single epoch of fine-tuning, all data sets, all models reached 100% contamination score. So this is good. This is exactly what we expect to see. Right. So another thing that is also important, if we think about verifying contamination in benchmarks, then we don't only care about whether the model has seen exactly this text that it is given. Because if, for example, someone is training not on the exact benchmark samples, but, for example, rephrased benchmarks, or augmented benchmarks, or maybe translated benchmarks, or some other changes to the original benchmarks, it still allows the model to bypass this question. It still allows it to cheat, but it is not the exact same sequence that that's present in the benchmark. So the question is whether the method can actually detect this kind of indirect leakage. And we found that if we train the model even on augmented version of a benchmark, we can still successfully detect contamination on the original dataset. So codec is sensitive enough to detect also this kind of indirect leakage arising from training on augmented, rephrased, or otherwise related data. Now, what are the possible applications of this stuff if we have it and we have certain confidence that it works? Well, first thing, of course, is to verify whether the benchmark evaluations are reliable. If you take any benchmark, like in this case, AMI24, and you evaluate what are the contamination scores of different models that are available on the market, you can immediately see which scores can be trusted, this with very low contamination, and which scores should be taken with a grain of salt. You know, if a model has a very high contamination score, if we can detect that it uses memorization a lot when solving a benchmark, it doesn't necessarily mean that the model is bad. It means that we shouldn't trust this benchmark evaluations alone, because the model may achieve high or low score, but it is very familiar with the benchmark data. So it doesn't necessarily reflect how the model generally approaches this kind of questions, but it means that this model is over-specialized for this distribution and this score may not transfer. So on one hand, it is helpful for improving understanding model evaluations. On the other hand, if we introduce a new benchmark, it is also a good way to verify whether the models are maybe already familiar with this, this kind of data that we use for evaluations. Because, you know, nowadays benchmarks do not necessarily use brand new data. They usually repurpose some existing data or generated data. So contamination, even in new benchmarks, is still a thing. Yeah, and because our approach is very simple and very lightweight, evaluating a single model takes just a few minutes. We evaluated a range of models from Hugging Face on multiple benchmarks. This is the table that we put in the paper, but we actually also host a live leaderboard with over 60 models on over 20 benchmarks. You can check the results. Guess who's on the top? Right. Further. Another thing that we can do with this kind of tool is to verify training and contamination and decontamination claims in the paper. Because, for example, Quen 2.5, in their technical report, the authors mentioned that they used training sets of different public benchmarks for training the model, but to ensure fair comparison on benchmarks, they also applied some heavy decontamination steps to ensure no overlap. You know, before you had no choice but to trust them that they did this right. Right now, you have a way to actually verify that. Because we found that Quen 2.5 on the train set of GSM-8K scored 100% contamination score. So yes, they did include this this data set in the training. But on the other hand, on the test set of GSM-8K, they score only below 30%. So this is really low. So that means that their decontamination pipeline was actually successful. So you can trust them. But you know, without this kind of verification, you never know whether this validation, this decontamination was successful, or maybe it was dummy just to say, oh, we do this, we train on this, but we do decontaminate, so trust us. And this kind of claims now can be verified. Yeah, if we compare different models, so far, only what we could do is to use a range of benchmarks and check whether the scores are better for one model than for another. But because of this contamination issue, all the scores could be inflated, and we had no control on that. Right now we should expect that if two models achieve similar scores on a certain benchmark, on a set of benchmarks, but one of them is considerably less contaminated with this benchmark, we should expect that it will generalize better to other data sets, because it achieves the same level of accuracy, but with much lower amount of familiarity. So it's like if you compare two students that solved the same exam for the same score, but one of them knew the questions beforehand, then, well, you should expect the other one is actually smarter. Right. Going one step further, if you're training a model, you are genuinely interested into what is the performance of this model, because you need to monitor the progress of training. But you never know whether some data sets may be leaked, maybe some benchmarks leaked into your training data. You know, training data is terabytes of samples, so you can never verify them like in detail, each of them, and extensively. So we found that already we evaluated checkpoints of Olmo model during training, and we found that already after 2% of the whole training of the Olmo model, Codex successfully detects the final contamination level of all data sets that we use for this evaluation. So already after 2% of the whole training, you can detect what will be the contamination of your model after it's trained. So if some benchmarks accidentally leaked into your training data, you can detect this very early during training and immediately take some actions. And avoid this kind of contamination that can further harden your model. Right, as I mentioned, this method is very simple. It is very lightweight. Evaluating a single model takes just a few minutes, so you can actually try it yourself. The code is available. It is an old book. Like, implementing this method is just a few lines of code, so feel free to try, feel free to run. Like, basic applications are already implemented. Right, so that's it from my side. So to sum up everything, benchmarking has some issues, of course, but with sufficiently good method, like for example ours, we can reliably detect which data was seen by the model during training, which was not, and based on that, we can actually understand what are the sources of model accuracies on benchmarks. And the method works for any gray box model. So for example, any model that's available on Hugging Face, and for any data set that you want without any tuning, and it is really lightweight and detects even indirect contamination. It is actually very useful and very easy to use, as you find yourself. Right, and that's it. I'm happy to take any questions if we have time.
Let's give a round of applause to Michał.
Thank you.
So, any questions? Okay, so over there first.
Thank you very much for the wonderful presentation on codec. I'm just curious to know, can codec answer the question? For example, if I'm an author and I just published a book and I want to know, did this LLM, was my book trained using, was the LLM trained using the book I published? Because, for example, if the book is copyright, then that should not be the case. Can codec answer the question if the book I've just published, which is a copyrighted book, was trained on the LLM? Thanks.
Okay, that's actually a great question. And the answer is yes and no. Well, no, because codec is not about the specific data that we use like for this evaluation. It's more about the distribution of data. So as we look at how it is computed, like we compute the score always based on differences between essentially two random samples. So they represent more the statistical behavior of the data set distribution. So we should think about this data set as a distribution of data, and the score reflects more the contamination with this distribution of data. For example, when we evaluated models on subsets of the pile dataset, they provide both train splits and test splits, so subsets that were used for training and identically distributed subsets that were not used for training. And on both these subsets, both the splits, codec scores are nearly identical. So that means that for identically distributed data, the scores should be identical, regardless of which one was used directly for training. Having said that, if your book represents a certain distinctive distribution of data, so for example, if we consider Harry Potter to be a certain distribution of paragraphs that is considerably different from other books. Like, of course, certain sentences might overlap because it is general English, but in general, the distribution of this book is to some extent specific because Rowling has certain writing style, because it involves certain, I don't know, character names, spell names, and stuff like this. It can be to some extent distinguished from other general types of texts. So, of course, it will be different from the general text distribution, and like this, it should work. However, this criterion is always statistical. It is a statistical criterion, so it shows you that there is a high statistical evidence that some text was used for training. It is never a proof, so if you go to the court, you can never say because of codex score being 100%, it is an evidence that this data set was used for training. You can never say that. I hope that answers your question.
So maybe actually to add to that, so actually we have also from our group, from CISPA, research about exactly this question to find out if a given data set, for example, as you said, a completed book, was used for model training. So you can also refer you afterwards to papers from our group that actually address exactly this problem. So maybe also regarding this question, also you also showed for the QN 2.5 that actually for the training set it had a high score for codec, and for the test set it has low score for codec, right? One of your slides.
You mean this GSM-8K?
I think for QN, yes, this one.
Okay.
So actually, so here it was on the top graph is for the training set.
Yes, this is training set, this is test set.
And so here in this case is different distribution of the GSM-K, that we have actually different score for the training versus the test set.
Yes, one thing is that because the authors of QN 2.5 they did some very heavy pipeline for investigating the overlap between those two sets, and they excluded everything that in any way resembled the test set. Then essentially they trained on a subset of train distribution that was as distinct, as separated from the test set as possible. So because of that, like their training distribution diverged from the test set of GSM-8K. And also for multiple models, you can see that these scores are actually, the distribution is actually lower than for the train sets. So we may expect that actually these two sets differ distribution-wise.
So also for all of actually these tasks, really what matters, I think, a lot is distribution of the data. It's one of the key points for this question. We have many more questions. Okay.
Thank you very much for your presentation. Am I right that if you rely only on scores, then you can also run codec on close to its models and check, for example, if Claude or Grok are trained on the phenomenon benchmarks? And I don't see Grok or Claude in your results board. Is there a reason on this? Have you looked at that?
Yes, that's again a very good question. When it comes to closed source models, all we require from a model to compute the score is to give us this measure of confidence for the given text. So for that purpose, we use average log prop. To get the average log prop on the given text sequence, we require gray box access to the model. So we don't need access to weights, we need access to logits for the given sequence. Typically, closed source models don't provide this access. So in this vanilla pipeline, we can't evaluate black box models, like fully black box models. Having said that, we also had some experiments whether this pipeline can be extended to closed source models, because we don't really care about what is this measure of confidence. This can be anything, like average log prop is one choice, but for example, if we instead choose average probability, this is also a good measure of confidence. And it turns out that for black box models, you can actually measure that, because if we consider a black box model to be something that for the given text gives us just the next token that it predicts after this text, then we can measure whether for each prefix of the given text, this next token matches the ground truth. And based on that, we get a binary label whether it matched or not. And if we average over the whole sequence, then we get empirical mean probability of correctly sampling the next token. So average prop, which is also a good measure of confidence. And we experimented with that. It is enough to compute codec scores. It is subject to higher variance, of course, because it is less precise, but technically you can apply this. But we haven't tried this because, of course, this kind of method is much more computationally intensive and less accurate. So we didn't run it at scale. Because of that, in this leaderboard that I linked, there are no closed source models. There are only Hugging Face models because they are the simplest, the easiest to evaluate. But yeah, technically you can extend this criterion to cover also black box models. But we haven't tried this at scale.
So my understanding is that the training benchmarks skew the results of each LLM, so of how accurate they are. So my question would be is why do they not use different benchmarking questions or different ways of benchmarking on each LLM every time?
You mean why don't we change benchmark for each new LLM?
No, but why do they not make new benchmarks for LLMs, or is that not the point of benchmarking?
Of course, we get new benchmarks every day. Basically, on each conference, we get hundreds of new benchmarks. The problem is that we need well-established benchmarks for this number to be meaningful. Because if you publish a new model and you say, okay, so here is a brand new benchmark that came out yesterday, and on this benchmark, our model is the best. Then actually nobody believes you, because what's this benchmark? Like, I don't know this benchmark. What does it mean at all? Why did you choose this one and not 100 others that also came out last week? Probably because you evaluated all of them, and on this one, your score is the best. So, there are also ways to cheat. And because of that, we use well-established benchmarks. So, for example, everyone cares about scores on MMLU, on, Asia Lee, on Terminal Bench, and stuff like this. Because these are well-established benchmarks, we know what they mean. We know that they are good, so we know that if a model is doing good on those benchmarks, it should do well in practice. Well, of course, except contamination.
Hello. Yeah, so thank you for the presentation. So according to my understanding, codec is highly based on what type of context you give with each data point, right?
Mm-hmm.
So what kind of context does affect the codec score? So is it semantic? It should be repetitive. Should it be related to the data set, a particular data point which you are giving? So what kind of context affects the overall contaminant score?
Mm-hmm, mm-hmm. Right. So when it comes to how we use this context, there is of course freedom. We choose to use the simplest possible form. So our data set is just a set of strings. So these are all just strings. We don't assume any structure in them. And to evaluate the sample with a context, we just concatenate all the context and the target sample. There is no fancy template, no explanation that you'll be given context, and now there is the target sample or anything like this. No, you just get some context sample, context sample, context sample, target sample. We also experimented a bit with what is the best to put here as this context. So for example, how many context samples, how long context samples, how to choose them. We found that it doesn't really matter. Like, there are some minor differences between them, but the simplest approach. So just taking a random context sample and just one. So comparing just the target sample without any context and with one context sample is enough. Like, it is the fastest way, the simplest way, and it works just fine. So that is what we use in our experiments, but technically you could also use 2 context samples, 3 context samples, and even more. Choose them smartly based on the distribution of this data set maybe. Technically you can do that, but we found that it doesn't matter much.
Mm-hmm. So you said that so do we sample like the samples, the random samples for the context? Are they also sampled from the same like data set that, for example, you showed this example of mathematical questions, right? And we want the context to also be mathematical questions. So where do we sample them from randomly?
Yes, exactly. It is important that they are sampled from the same data set. So for this whole evaluation, we use this LLM that we are given and this data set that we are given, and it is everything that we use. We don't use any external data because for this context to be helpful, you should assume that there is some mutual information shared between those samples, because otherwise there is no point in assuming that this context may be helpful in some cases. But if we use sample from the same data set, then as I mentioned, like each data set, it's not a random collection of like string sample from all possible places. Usually they have certain structure, they share certain types, vocabulary, and so on. So even just a tiny bit of shared information is enough to improve the confidence of the model on this target sample. So we always sample from the same data set to ensure this information sharing.
Okay, maybe this is last question.
Okay, so you focused later on accident and contamination, but at the start you mentioned as problems that there is really no penalty for purposefully contaminating the models and just cheating on benchmarks. Considering that codec methodology is pretty simple, is it not easy to cheat in the same way, just also as to the training data multi-sample inputs?
Yes, of course, if codec is known, then technically it is possible to cheat, to train the model against codec, so to make it contaminated but appear to have low codec scores. Of course it is an issue, but firstly, the moment that we publish this paper, nobody knows that such a method exists. So it is definitely valid for everything that was published so far. Well, secondly, if the model, if someone who trains a model finds a way to train a model in such a way that even though the model is contaminated, it can successfully leverage the context, this is in some way an improvement of the model. If someone, for example, tries to train a model to forget the samples to reduce this contamination, then they lose this advantage of inflating the accuracy scores on the benchmark. So the question is whether anybody will be willing to sacrifice benchmark performance for this contamination detection. Of course, it also introduces another layer of complexity, additional compute that is required to train a model, for example, on backward gradients through this pipeline. Will you be willing to invest this compute? Maybe yes, maybe no. But if you'll be willing to optimize against this objective, then I can always change it. Like instead of one sample, use 3 context samples, or tweak some other parameters, or how the context is chosen, or something like this, and good luck in optimizing against all possible choices here. Of course, there will be definitely some ways to cheat this criterion. In some time, if it will be widely used, it will become obsolete soon. But of course, as LLM training pipelines change, contamination detection methods will also be improved. Based on that, I expect that even more successful methods can be built that will be resistant to various types of adversarial approaches.
Okay, thanks a ton, Michał, for the great talk.
Thank you very much.
All our questions. Let's give to Michał a round of applause. Okay, So you've just heard that Michał worked on this problem for LLMs. However, we have here only 24 hours, so we ask you to work on a very similar problem, but in a simplified setting. So here the main point is that we are giving you training data sets and also a model, and the question is how much was used. So how much of the data set actually was used to train a given model. And in this task number 1, we ask you to give a continuous score from 0 to 1 that expresses how much of this training data set was used to train a given model. So it's not only about if it was or not, but we ask you the question, really, how much? So what is the task setup? So we have this blue database data set of so-called mixed data set, which was used to train many ResNet models. We have 3 types of ResNet models. We have ResNet 18, ResNet 50, and also ResNet 152. And we have, for each of these ResNet types, also we have model ID. So for example, ResNet 18 models start from the prefix 0, ResNet 50 from 1, and ResNet 152 from 2. And your task is that for each of these models, you have to provide a continuous score. We call it a Ducci score that expresses how much of this mixed data set was used to train each of these models. So what is given to you as artifacts for this task is the following. We have data sets which are based on CIFAR 100 data set, and we have 2 data subsets. We have this mixed data set, which actually is containing 2000 images with also corresponding labels, and we have here 100 classes. Also, we give you so-called population data set, which contains 10,000 images from also the same 100 classes. Now, how do we measure in this task your score? So here we use the simply mean absolute error for each model I. So we compute this MAE score, which basically is absolute value of the ground truth, so our known contamination, so how much data actually was used to train the model, minus your estimate, so your score that you provide to our API. And then we average this score across all the models that actually used in this task. So here for you we have simplified version with 9 models. We have time to really compute these scores, and we measure this mean MAE score. And actually this score also is displayed in our scoreboard. So if you see our scoreboard, task number 1, then if you submit your solution, then you will see actually exactly this mean MAE score in our scoreboard. So any questions to the first task? Crystal clear?
Also,
Okay.
you'll have more, like you get the task description, and if then later on, once you start really thinking about it, there are questions coming up, you can always ask them on Discord. Otherwise, let's move on to the second task. And we've now looked into recognizing distributions of data, recognizing fractions of data. But the second task focuses on individual data points. So we all know that these days we have great models that can, for example, generate photorealistic images and amazing text. But these models, to achieve their performance, are trained on that data and therefore incorporate that data. And as Adam has already mentioned at the beginning, this currently causes a lot of lawsuits regarding copyright of this data, because the models can reproduce their copyrighted content at inference time. And it has been shown actually that especially for image generative models or for models that work on text and images, this is particularly severe, because if you have such a model in the training or such a data point in the training data, then at inference time, if the image is memorized, you just give a prompt like that, a cat in an office, and you get the same cat out. And of course, this would be then a copyright violation. So now let's briefly look into these complex models, how they are trained nowadays. So these models have different pipelines. Often models are pre-trained on pure text. So we start off with a powerful language model, and then afterwards instruction fine-tune that to be like more behaving for some certain tasks. Then we do some vision pre-training, where we now introduce this image modality. And then there, like depending on what type of model you want, either some speech pre-training or a multi-model adaptation. And for example, what you could use here is like different text stories, dialogues, images and bios, or even some Q&As to get the model really started of understanding this intersection between modalities. Now, what's happening is that at each and every single modality, sensitive information like private information or copyrighted information can be introduced and then be outputted by the model at inference time. So like just to give you an example, if in the text pre-training stage I introduce my phone number to the model and the model memorizes that, when somebody interacts with the final model, then the model might output my phone number. And just to talk about a bit the underlying reason is that the model learns to finalize, basically to terminate sequences. And therefore we distinguish between like some prefix of a sequence. Here, for example, my phone number is, and the suffix, which in our case is the private information. And then the question is, if we give the LLM this kind of prefix, can it correctly finalize the suffix? And if it can, then we call it memorization. There's a bit of a caveat to that, because if the prefix is very small, then the model probably can't continue, so it's not enough information to trigger this memorized content. And if we give a too big prefix, then it might be trivial for the model, because it's not really truly measuring the memorization, but it instead kind of like nudging the model to output exactly what we want it to output. And so your task is now to nudge models to output sensitive information. And therefore, we will give you a large multi-model model which has been trained and intentionally overfitted on some text-to-image data, namely visual question answering. So it has been trained on these kind of profiles, which have a profile picture and then some sensitive information of people. And then the Q&A part of that trains it to answer these questions. Like, for example, here, what was Gabriella Johnson's credit card number? And then the model knows this still from the training. Now, with given this image to tell this card number does not necessarily imply memorization. It's just OCR, like asking the question, can the model read for it? So to really test memorization for your task, we've basically hidden that information. So during training, the model saw that information, but then the images that we give you have this masked, such that the model would have to complete it from memory. And we'll be providing you with 2 sets of data, namely first an evaluation set. This is the set that you'll be finally being scored on. And there are thousands of these examples, like an image, and then the scrubbed PAIs, and 3 questions regarding 3 sensitive information, like the phone number, the credit card number, and so on. You're additionally given a validation set. This is a non-scrubbed set, so this is just for you if you want to train some model to learn, or if you want to validate an approach, you basically have the ground truth there. This is going to help you. And you get your target model, which is the large multi-model model. And finally, you get a so-called shadow model. A shadow model is basically the same type of model, same training pipeline, but instead of being trained on the model with the full PII, it has been trained on the data without PII. And you don't have to use this model, but it might be helpful for you. And we pre-trained it for you such that you will have the opportunity to use it without spending too much compute budget. And what you will be submitting at the end is a CSV file with 3,000 rows, namely 3 types of PII per each of these 1,000 samples. And the first column will be the ID, so the user ID of this particular sample. Then there will be the PII type, so you're indicating which PII you're reconstructing here. There are the 3 options of the email, the credit card, or the phone number. And then your prediction of this particular PII. And how the score is defined is a similarity score, namely it's 1 minus the normalized Levenstein distance of the original PII versus your predicted PII. And if your similarity is 1.0, that means you're able to perfectly extract. And if the score is 0, then no successful extraction was done. And just a small recap, of course you can look that up more in detail, but the Levenstein distance, what it does roughly, is to measure the number of single character edits that are required to change from one string to the other. So it kind of measures string similarity, and that makes sense for us. If you want to extract something, it should be as similar as possible. And just to give you an example of like the Levenstein distance between the word kitten and sitting is a Levenstein distance of 3, where we basically have to first exchange the K for the S, then this E here for an I, and eventually we append the G. So like any addition, replacement, or removal of character counts there, and the Levenstein distance is this minimal number, basically. And at the end, the score is going to be averaged over all the samples, and you're able to submit here every 5 minutes. So once you submit it, then there's this cooldown time, because otherwise like people might be able to brute force. They're just like simply trying out the strings. So there's this cooldown. There's one good news. If you have an invalid submission, which means like it was rejected because the file was misformatted or so, or like the CSV wasn't in the right shape, then I think this cooldown is only like 2 minutes to not penalize too much, and then you can just retry more quickly.
Any questions?
So where can we access all the presentations that we had before? In the Discord channel?
Yes, everything is uploaded on Discord.
Thanks.
All right, otherwise let's move on to the next task.
So now let's go to the second part, third task in this hackathon. So we talk about input data to the models, we talk about how models train on this input data, and now we go to the output side from the models. Before giving you the task itself, first let's talk about how really LLMs work, how they predict the next token. So we have here the simple example. We have the token this, and the model then predicts the second one being is as the next token. And then we append this is as the next token after this, and we ask LLM to generate the next token. LLM then have inside this vocabulary of many possible next tokens, and then also during this generation also assigns probabilities per a given token. Then if we go for the brute force, basically the maximum probability prediction, we just in this case would take this token fine as the next one. So we just predict in this case the tokens with the highest likelihood. Now, how can we really mark this output data? So how can we add some form of watermarking to the output to later find out if the text actually was generated or was human created? So there is this very famous nowadays scheme called red-green watermarking. How it works is that we divide this vocabulary into two subsets with green and with red tokens. And then during the generation, if we don't watermark this text, then we just choose randomly one of the tokens from the vocabulary. However, if we watermark the text during generation, naturally we bias the model to select tokens from this green list. Now, this is a simple example how this looks. So the top text is non-watermarked, so-called clean text. So if you just analyze how many tokens are green versus red, you have roughly the same number of tokens from both lists. However, if during generation actually you do watermark your text, then if you then analyze these tokens in the watermark text, and most of these tokens actually they come from the green list. Now, in this case, what we show is that if we again would have this input prefix this is, and then we have the next token to be predicted by the LLM. So in this case, since the token fine is in the red list, we wouldn't choose this token, but we would choose rather the first token in the green list, which in this case would be great. To give you more intuition how the algorithm really works behind the scenes to watermark the outputs from LLMs, here is the algorithm. So first we have this line that we get the probability vector, as we discussed, per a given token. Then in the second line we use previous tokens to generate a random number. And then we use actually this random number to then split this vocabulary into the green and red lists. And finally, we sample tokens with the bias of the LLM to choose these tokens from the green list. So then we perform statistical tests to analyze if a given output text is watermarked or not. So if most of the tokens actually in the text, or statistically more tokens are green, actually we mark this as being watermarked text. Otherwise, we state text is non-watermark. And here is an example. So we have watermarked text on the left-hand side versus clean text on the right-hand side. Now, your task actually is to differentiate between this watermark versus clean text. So we give you some text sample, and then your actually task is to assign a continuous score, again, in the range from 0 to 1, to then state if a given text actually is watermarked or clean, non-watermark. If your score is equal or above 0.5, this actually denotes that the given text is watermarked. If the text, if your score is less than 0.5, this actually would mean that actually the text is clean, non-watermarked. Now, what is the score for this task? How to evaluate your scores? Your solutions. So we take this true positive rate and low positive rate. In our case, here being 1%. So we have positive as being watermarked text and negative as being clean, non-watermarked. And then we compute these counts for, in this case, if the text is watermarked and you mark this as being watermarked, this is also true positive case. And we basically compute these TPR scores and then FPR scores. We also select the threshold so that given your scores, we find out at which threshold we have FPR of 1%. And actually then from that we compute the true positive rate. And then high TPR denotes that you have also high score, meaning that you correctly identified watermark text. What are the artifacts for this task? So we have to you provided this dataset.zip file with actually internally 3 splits. We have a train split, which actually contains 360 samples in total, 180 of them with clean, 180 with the watermarked versions. Also, we have validation split. So here we have 180 total number of samples, 90 of them clean, 90 watermarked. And also we have for you test split to now for this 2,250 samples to provide your scores. So then you have to, for all of the samples, provide your score from 0 to 1 to denote if a given text is watermarked or not. And then once you have these scores for these 2,250 samples, you just submit a CSV file with 2 columns, ID and score. So ID is the ID of this given sample and score from 0 to 1 if the text is watermarked or not. Any questions regarding task 3? Okay, there is one.
Are we going to have also access to the hash function and the random generator, or is it like more like training a model that's...
Yes, a very good question. So actually in the task we also actually give you the references to papers that show how to watermark text, but we don't give you access to the random number and that we are also using for the watermarking. And then it's more like natural task, right? So, you know, if you're a student and you would like to find out if your solution is generated by LLM or not, then you would like to really do it without even knowing what is the random number used for the watermarking. Very good question. Any more questions? Okay, so also to make sure that you have enough compute to solve the tasks, we actually have for you here GPUs from our compute center in Germany, from Jülich. They were so kind to offer many 800 GPUs, so all of you have enough resources, enough GPUs to work on these tasks. So if you haven't done it yet, please register at Jülich. Also, it's easier for us if you use your university email address or from your company, then we can easily just accept you and you can just access these GPUs. So here again, use multi-factor authentication to access the Jülich infrastructure. You have to also accept user agreement so that you just focus on working on the task using these GPUs. You can use your SSH key and generate a new one to access this API. So basically you just do SSH to the servers. And then also, if some of you have still access problem, then you can now actually go again and check these IP addresses. You just copy them, and then you are able to access these Jülich servers. Then, if I haven't accepted you yet, please wait a few minutes, and after that, servers are updated, and you can access the GPUs. So here is how to connect to Jülich. So once you have the account, you just do SSH, specify which key you use for the connection, and you are there on the servers. Now, how to work on the tasks. So most of you, we know that you use VS Studio Code. So here is a very, very short recap how to use the tool. So you usually would work directly on the servers of GPUs. Just go to the bottom left corner, SSH connection. You can just choose a host. If you are not still there, you can create a host for Jülich. So here is the lines to just copy paste into your config file. And then you can just specify that you want to connect to Julish. Once you are there, you can just start a new terminal. In the terminal, you can just execute the specific per project 2615 for our hackathon today. And what we recommend for installing packages with Python is UV. Is by all means the fastest tool. And copy-paste also these commands for bashrc to be able to easily access UV and all of this cache config. And then set some commands to get you started. So create, for example, UV environment, add packages. Now, what is here the crucial part is to use GPUs. If you want to use this large structure, then you have to create this bash script for the sbatch job. So actually we use Slurm on these servers. So this is actually the file that actually you can use to use this large-scale infrastructure with many 800 GPUs. And then there are some key components of this, for example, like what is the reservation for today. So you can just copy-paste from this slide, and then you'll be able to access this large number of GPUs. Once you have this script, you just do sbatch and submit this script. And then you have this access to, per node, we have 400 GPUs. Any questions?
Of course, we'll also be there around in the first hours to help you set up this GPU infrastructure. If there are any questions that arise, just let us know. By now, we are experts on how to use that cluster. Otherwise, I think we can just have the last thing. Namely, there are still many single or two people participating teams. And I mean, while that is perfectly fine, I think like with that, you won't have a chance to win because it's 3 tasks. So what we really recommend is that you merge. So Julian over here, like everybody who still needs a team or is a team that wants to adopt some like 3rd, 4th person, please meet over there, merge into a team, and then Julian will update that. And once all the teams are stable, you will get an email from me. So now that this hackathon is a bit particular in the sense that we have many people who are not yet in a team, so it's a major restructuring. We need to like identify what will be the final team number. So once those are determined, then you will get an email from me, and this email will tell you your team number. So like we will, from your team name, then derive your team number. The team number determines which will be your desk in the rooms upstairs. And you will also get the access token from the API. Each team gets their own access token that is shared between all the participants. The timeouts are per task. So if your partner is submitting in a different task and you're submitting in your task, then like their submission doesn't like let you cool down, but instead it's per task. There's one thing which is very important, which is that teams are not allowed to collaborate, because this gives you an like unfair advantage. So if we see any collaborations between teams, these will be disqualified. So just as a heads up, the teams are here competing each on their own. And but you're more than welcome to now like stock up your team with enough manpower, woman power, and then get started. Are there any questions regarding the further setup? Otherwise, then grant us this like half hour to sort out who's in a team with whom, and then send out the emails. And then, like in the meantime, you can get started, you can get familiar with the infrastructure. Adam's going to upload the slides. And good luck, everyone.
Good luck and enjoy it.